from mechanics. Yeah, Ganesh, I'm starting with that question only. Starting with a question from mechanics, which Ganesh has shared. So although I'll be prioritizing the modern physics doubts today, but I will start with this particular question, which is in fact from mechanics. So this particular question is like this. There is so there's basically a surface like this, which has been given a layer of viscous liquid. Okay, so something like this, a two-block system, but the difference is that this block of mass small m is placed on a plank of mass capital M and length L. Now it is placed on a lubricated surface, whereas between these two, the coefficient of friction is mu. So the lubricated surface is such that it offers a resistive force. The viscous drag force is proportional to the speed of the plank. So it offers a resistive drag force, which is, let's say, alpha into V. This is a viscous force. It applies like this. Okay. Now, initially at t equal to 0, what is happening is that the block is imparted a velocity v0. So you're applying a sharp impulse, which is giving this a velocity v0. Okay, so we have to find the total distance slid by the block relative to the plank. The distance slid by the block relative to the plank. And we have to also find out the total distance slid by the plank. Okay, so there is no force applied, Aditya, in this particular question. Yeah, I've got your questions, thanks. In this particular question, what is happening is that we are giving a sharp impulse, J, at t equal to 0, so that this block develops a velocity v0. So that J is like a collision impulse. It's F delta t, where force versus time, like this. So it's a sharp amount of force applied for a very short duration of time. This kind of situation. Okay, so let's understand what happens over here. So for some time, there will be relative motion between the two. Okay, and eventually the two will be slipping together. And even as they slip together, eventually the whole system will stop because of this viscous force which is acting. So to 0, what happens is that the block A has a velocity v0, and as a result of that, there is frictional force mu mg acting on it. So it has an acceleration of mu g, or rather a deceleration of mu g. Okay, and because it's t equal to 0, the block B was at rest initially, so its velocity is 0. So at that moment, there is only one force acting on it, mu mg. So it develops a forward acceleration of mu m by capital M g like this. Okay, whereas this develops a deceleration like this. Now, eventually, after some time, A's velocity has become v1, and if we assume that still slipping is going on, A is still decelerating at the rate of mu g, but by developed a velocity v2. So now the friction is wrong here. Yeah. So B will now develop a second force also. Okay, so there is kinetic friction here, which is mu mg. Now the second force acting on B is the viscous force, which you can say is alpha V, like this. Okay. And B's velocity is, so B's acceleration is going to be this kind of a term. Okay, so if you look at this, A's velocity as a function of, so this second picture was at a time t. This was at a time t. Okay. Now V1 as a function of time will be mu gt, whereas V2 as a function of time will be such that dV by dt is in fact V2 only. So this instantaneous velocity I'm taking as V2. So V2 as a function of time is such that the rate of change of this is, okay, this. Okay, so this equation is of this type. Let's say, it is some P minus QV, where P is a constant and Q is a constant. Okay. Now these two equations will be valid till what happens? Till V1 becomes equal to V2. Till V1 is equal to V2. Okay. Now after that time, okay, V1 remains equal to V2 such that some common velocity, and that common velocity starts reducing at the rate of minus alpha divided by m plus m, because the static friction makes sure that V1 is equal to V2. So now you can make a combined free body diagram of them and solve this. Okay. So make use of these equations and try to find out this. Okay. Make use of these two equations and divide the motion into two parts. Initially, when V1 is not equal to V2, till V1 becomes equal to V2. And eventually when V1 becomes equal to V2 but continues to decelerate, they have a common velocity V which is decelerating like this. Ganesh, are the equations clear to you? Okay. So see what we'll get for solving the second equation. So from the second equation, we'll get something like this. No? V2 will be equal to like this. So 0 to V2 times 0 to T okay. So P was, so P by Q over here become alpha, sorry, mu mg divided by alpha. okay, into 1 minus e raised power minus q, which is this is what we are getting v2 as a function of time, whereas v1 as a function of time is this. Yeah, sorry, this will not be, this equation will be v naught minus, okay, so v1 will be v naught minus mu gt because it has the initial velocity. Okay. Now, firstly, in the question, you are just given that the velocity is proportionate. I mean, the viscous force is proportional to the velocity. It is not even given that what the constant of proportionality is. So alpha is an unknown term for us here. So the answer cannot be, yeah, the answer cannot be independent of alpha. Anyway, so what will happen is that you have to first find the time when v1 becomes equal to v2. So when v1 becomes equal to v2, this term, it will become equal to v naught minus mu gt. Now this equation is not something simple to solve. Cannot really solve it that easily because it is a combination of, it's a transcendental kind of equation. But however, if we assume assuming that you know alpha t by m is small compared to 1, then you can use the series of e raised power minus x. You can use the series. Yeah, Samik, the question is above. You can go through this question. I'll just send the question on the groups also. So you can go through it. Yeah, so I've just sent the exact question on the group, so you can go through it. Yeah, so coming back to this, you can probably do a solution if we assume that this time is such that alpha t by m is small compared to 1. Then you can do that Maclaurin series solution of this. So that will be one. This kind of series, right? E raised power xs. Minus, yeah, sorry. There are the odd terms also, no? So it is basically f naught plus f prime on and so forth, this kind of series, right? So yeah, so it is this kind of series. So assuming this is small, we can approximate this as 1 minus x. Okay, we can neglect the higher terms. So if we can do that, then probably we can get away with this. Mu mg upon alpha. Okay, but this is with that assumption that alpha t, with that assumption that alpha t by m is very small compared to 1. Okay, so then we'll get this. So then you can see the displacement of this one with respect to the Planck. I mean, then you can solve it. So this is the time when, this is the approximate value of time when slipping stops, slipping between the block and Planck stops. Okay, Ganesh. So if you have the answer key, you can just check whether this will give the answer or not. Because without this assumption and without this approximation with the given data, there's no way we can solve further. So I mean, this is a general series, but this is the approximation that we are using here. The general function, but we are using this approximation. Okay, very good. So we'll come to the second part also. Okay, second part also we will use some kind of approximation. Okay, but let me explain the whole thing to everybody once more. Okay. So let's go over what we have done till now. So we made the free body diagrams of the block and the wedge at some general time t when slipping is occurring. So these FBDs are when V1 is greater than V2. So they are slipping at that point of time. Okay. So from that we are getting V1 as a function of time like this, and we are getting V2 as a differential equation function of time like this. So this differential equation had to be solved. So that solution of that differential equation, you can see that rate of change is a linear function. So you'll obviously get that exponential relationship. This is like the discharging of capacitor, like the charging of capacitor, or those kind of differential equations. Okay. So your velocity V2 as a function of time, according to this, your V2 as a function of time should be going like a graph like this. Should be going and eventually achieving some steady state. But here that will not happen. It will not go up to the steady state because your velocity V1, which was decaying with time at a uniform rate, that will catch up with V2 at some point of time. And after that, what will happen is they'll have a common velocity, which will then eventually decay and eventually tend towards zero, something like this. Viscous force work done will not be zero sum. Viscous force though is this thing, no? It is a non-conservative force. All drag forces are non-conservative. In fact, there are very classic questions to show how viscous force is non-conservative. I'll show you an example of the demonstration why viscous force is non-conservative. But anyway, okay, so for everybody else, I hope the solution of the differential equation is clear up to this step. No? This is how we got V2 as a function of time. This one. So this V2 as a function of time is basically like, if it was allowed to proceed for a lot of time, it would be some terminal velocity into 1 minus e raised power minus t by tau kind of term. The tau is that constant in this case, m upon alpha. But here it is not allowed to go all the way to terminal velocity, because before it goes to the terminal velocity, V1 and V2 become some common velocity, and once we see it becomes a common velocity, from there it will decay with time. Okay, so we're coming to that part. So now we wanted to find the time when this thing slipping stops. So that's the next part. So we've got V1 as a function of time, we've got V2 as a function of time. Next, what we're doing, we're trying to find the time. This is when slipping stops. Okay, so that we can answer the first part of the question. So to find that time, we have equated the value of V1 with the value of instantaneous V2. Okay, and then we have used this assumption here that this term, the power of E, this term, this one, this is our X, it's small compared to 1. So 1 minus e raised power minus x, we are approximating as x, because we are neglecting the higher terms. Okay, so this whole term 1 minus e raised power minus alpha t by m, we are approximating this as alpha t by m, because we are assuming that alpha t by m is small compared to 1. So with that assumption in mind, we are getting this as the value of time at which the slipping stops. Okay. Now coming back to the first part of the question, we want to find the displacement of the block in the frame of the wedge. Okay. So in the frame of the wedge, what was happening is that from t equal to 0 to t equal to v naught by 2 mu g. Okay. What is the relative acceleration? Acceleration of the block with respect to the wedge. That is how much it is, A1 plus A2. Okay. So the acceleration is equal to, so basically the block was having a backward acceleration in the ground frame, A1 like this, equal to mu gt. Okay. And the wedge was having a forward acceleration in the ground frame of minus that alpha v2. Okay. So it might actually just be easier to find the individual displacements. Anyway, might just be easier to find the individual displacements and subtract them. Instead of going into relative motion, here let's calculate their individual displacements. So if this was a situation at t equal to 0, where this started with v naught, this was at rest. So after some time, let's say this is the situation now. So this one has made a displacement S1, and this one has made a displacement S2. So S of the block with respect to the plank will just become S1 minus S2. That will be easier, I think. Okay. So S1 we can see will be V naught minus E1 t. Now we are taking this time as the specific time, v0 by 2 mu g. Okay. So what has happened? This one's velocity would have become v0 by 2. I mean, I'll come to this. Okay. Sorry. At this instant, v2 is equal to v1. So v1 equal to v2 would be this. Okay. And this s1 would be how much now? Uh, we can take the average of v0 and v0 by 2. So that is 3 by 4 v0. Okay. And multiplied with the time. So that was so v0 3 v0 square by 8 mu g. This should be s1. You can also check it by ut minus half at square method. But what I've done is just I've taken the average of v0 and v1 because it's a uniform deceleration. So we can just use average velocity. So v0 and v0 by 2's average is equal to 3 v0 by 4 and multiplied with the time. So that should give you the displacement. Whereas S2, I will need to calculate. So for S2, we have this relation that V2 was equal to some terminal velocity 1 minus e raised power minus alpha t by m. Okay. And that terminal velocity was this kind of relation mu mg by alpha. Okay. So S2 will become this kind of term now. Okay. In general, and we'll substitute the value of time as the above one. So S2 will become Vt into T minus okay, 0 to T. This kind of term it will become. Okay. Now again, assuming that alpha t is small compared to 1, we will equate this with minus alpha t by n. So this is approximately but then we'll get this displacement tending to 0. Yeah, and that makes sense because or we can try one more thing. I mean, see, to avoid making it 0, we can take the first two terms of the series. So, this 1 minus e raised power minus x, we can approximate it as instead of x, we can also take the second term, which will become this. So either we can do that or we can do the approximation at this stage only. here only we can approximate 1 minus e raised power minus alpha t by m as alpha t by m. So this thing, instead of this, it just becomes yeah. Now that time was equal to how much was it? V naught by 2 mu g, right? So we'll substitute that later. So our VT, V terminal, was this term mu mg by alpha. So this becomes this kind of a term. So this becomes mu g into V naught square by 8, and this term will cancel out with. Okay. So we will get the displacement of this one. So you don't need to do these steps. You're just approximating this term here as this. So this integration is directly becoming this. So our S2 is approximately becoming V naught square by 8 mu g. Okay. And S1 we had calculated above. Okay, so just go there. Where was S1 now? Yeah, S1 was this 3 by 8, and S2 is 1 by 8. So S1 was 3 by 8 V naught square by mu g, and S2 is this approximately V naught square by 8 mu g at t equal to V naught by 2 mu g. Okay, when slipping stops. Okay, so the relative displacement, that is S1 minus S2, will become V naught square by 3 by 8 minus 1, so that's 2 by 8 or 1 by 4 mu g. So again, Ganesh, if you can check this answer. Yeah, we will come to total displacement of Planck. Okay. But the first part is to find the displacement of the uh, block with respect to the Planck. Okay. So I hope all of you understood why this will be that displacement. Because after this, there is no more relative displacement. Okay, Samyak, I'll check. Okay. So Ganesh, if you can just confirm, does this answer match with the answer key you have? Yeah, okay. Now let's come to the second part. अभी second part के लिए क्या करना है ना, Planck का total displacement निकालना है. So now what we have to do is from t equal to this value, V naught by 2 mu g onwards. What is happening is that this and this are like one common object. Okay. So at this time, they have this velocity, let's say whatever, v1 equal to v2, whatever velocity that was, it was in fact v naught by 2, if I remember correctly. And now this kind of viscous force is acting, and between them there is static friction. So that always makes sure that they are, sorry, now static friction will like act in such a way that it is self-adjusting. So on this one it acts forward, on this one it acts backward, such that the system will have a common deceleration. Will have a common deceleration. Okay. So at any general time t, now the whole thing has a velocity v, and on the whole system, the external force is only alpha V, which is the viscous force. So it has a deceleration, which is alpha V upon m plus n. Okay, so this is going to give us that exponential kind of thing. Okay. So we can do one more thing. We can reorient our clock. We can say that at this point of time, let's say time is 0. It will just make it easier to solve, and this is some time t. So this was V naught by 2 at capital T equal to 0. And this is becoming some V at capital T equal to some time t. So this is the velocity at a time t, which is actually the total time minus V naught by 2 mu g. Because our time t was equal to V naught by 2 mu g when I've taken the second variable of time as 0. Okay. So now at some time t, the second variable of time is actually t minus V naught by 2 mu g, like this. Okay, so this kind of thing. So now we can see that the total displacement. So you can see that here V tends to 0 as capital T tends to infinity. So the total displacement will be integrated from 0 to total T tending to infinity. Okay, so now the problem is we have an alpha term again. Some other approximation had to be done. So the net displacement of the Planck will become the displacement of the Planck from 0 to, T equal to 0 to V naught by 2 mu g, which we just calculated above, plus the displacement of the Planck from capital T equal to 0 to infinity, this kind of term. So this was that V naught square by 8 mu g, but this is having that term of alpha. Ganesh, is there an answer for the second part also that you have available with you? No, Swamitip, we cannot apply momentum conservation, no, beta, because there is viscous force as acting as an external force. If the ground was frictionless, all those things you're saying are correct. But then the problem would be very simple. Na? It would be uniform acceleration and uniform deceleration till the slipping stops. And once the slipping stops, it would be uniform velocity for the system. But here there is that viscous force. Na, beta? So we cannot apply momentum conservation. Following, there's a more complicated question than that. So how you will calculate impulse due to viscous force? Impulse is kx. But impulse is force integrated over time. Na? Oh, right. Okay, so kVdt integrated. Okay, we can try that. Let's take the suggestion that Somadeep is giving here, that if we apply impulse momentum to this system, if from this time where this was v naught by 2 mu g, so this had a common velocity of v naught by 2 till the velocity becomes 0. So for this, correct. So we can apply that. Very good. So what is happening is during this time, the external force is alpha v backwards like this. Okay. So the impulse due to the external force will be minus alpha v dt integrated from 0 to some time, let's say capital T. And this is the change in momentum of the system from 0 to capital T. Okay. So this is minus alpha v dt integrated from 0 to t, and that is going to be the change in momentum, which is minus of m plus n. Yeah, so see, this is giving us the same thing which I've got by integration. So this could have been done by a much shorter thing. So this will be the total displacement. Okay, this total displacement only. Yeah, so we could have avoided that lengthy integration. But the thing is, the answer is still going to come in terms of alpha, and alpha was not given to us in the question. So I was just wondering if we could have done some approximation and a different method to avoid alpha, but I don't think we can, because alpha becomes significant in the answer. So now the net displacement of the plank from 0 onwards, from t equal to 0, okay, to stopping point till it stops, okay, that will become again velocity displacement initially, which we had calculated, which was v naught square by 8 mu g plus this term. Yes, so this is a very good shortcut that you can apply here. This is a good suggestion, Somadeep. So when we have a force which is proportional to velocity, then it's very easy to calculate the impulse due to that force over a certain time in terms of the displacement, because alpha v dt integrated simply becomes alpha into the displacement. So this is a very good little trick here, that this v dt, it just integrated, it just becomes a total displacement. But the problem right now is that it doesn't help us further with this question because that alpha is unknown. So Ganesh, do you have the second part's answer available with you? If it is, it should be in terms of the proportionality constant alpha. So what is the answer given for the second part, beta? Yeah, we can apply this from the initial also. Oh, so if we apply it from initial, maybe we can get the value of alpha in terms of mu g, is it? Yeah, we can try that. Okay, let's see. So another thing we can do over here in that case is, what if we try applying this impulse momentum concept from t equal to 0 itself? So from t equal to 0, when this one had a velocity v0 and this one was at rest, from then only this impulse force started to act. Okay. But the problem then, is what? That when we write this alpha v, na, this represents this one's velocity. Okay. And this one's velocity is not equal to the system center of mass velocity. You're understanding the point? So when we apply the impulse momentum theorem, na, we can only write ds is equal to v dt if this is the velocity of the center of mass and this is the displacement of the system center of mass. So I think this will become a little complicated, because if we try to apply it to the lower block, then we'll have to take the frictional force into account. So it might give us a simpler way of calculating that displacement as 3 by 8 v naught square by mu g, but it will not really give us anything further. So I would suggest that let's assume the question has given us that proportionality constant alpha. Okay, and then our answer according to the value of alpha or that proportionality constant is this much. This is the net displacement of the plank. Okay, or unless the question is asked, is the question asking total displacement of the plank, or yes. Okay, so that's the conclusion then. That's fine. Okay. Now, okay, I'll pick up another couple of questions before we start with the modern physics set of questions. So I'm sending another question set in the group. Okay, please go through this question. Yeah, Soumyadip, I'll come to your question. But before that, let's quickly wind up this other question. So, it's showing a graph of electric field. Rather, it's showing the actual geometry of electric field lines in the XY plane. And the electric field lines are something like this. Okay. Now, it's also saying that the electric field lines are symmetric about the y-axis. So that means, They are symmetric for rotation with respect to the y-axis. Okay, so these are electric field lines. They are symmetric for rotation about the y-axis. So that is what will show you that because they're symmetric, that means at such a point the electric field will be like this. At such a point the electric field will be like this. Okay. Now they've also given us some indication where we can count the number of field lines between x equal to 0 and x equal to 5 as 5 field lines. Like this. So the 5 field lines here, and those spread into so these 5 field lines, by the time they go here, this is x equal to 15 and y coordinate is 10. Okay. So now basically what we have to do in the question is that you have to find the equilibrium condition for a particle when it is at y equal to 10. So at the point 0, 10, okay, the electric field is going to be some E10J cap, let's say. At the point 0, 0, the electric field is some E0J cap. Now this E10 will be proportional to what? The density of field lines. So imagine what you're doing now is that at the point y equal to 10, you cut a disk like this. You cut a disk of radius 15. Okay, so the number of field lines going through this disk is proportional to 5. So this is proportional to some number of field lines, let's say delta n, divided by 2 pi into 15 square. Whereas the same number of field lines below, at your near your origin, the same number of field lines are going through a disk of radius only 5. So E0 is proportional to that same number of field lines divided by divided by pi, area of disk. So this is pi into 15 square and this is pi into 5 square. So the magnitude of electric field ratio at these 2 points will be 9:1. Okay. So the charge, I think, should change by a factor of 1/9, so that the electrostatic force is the same magnitude and it balances mg. Okay. Is the question clear? I hope all of you have gone through the question first of all. This is the question I've just sent you on the group. So you have to change the charge to 1/9. That means the fractional charge change in charge will be what? 1 minus 1/9 divided by 1. So it will be 8/9. No, it's saying the estimate the fractional change in charge. So that is the charge has to become 1/9. So the fractional change should be 8/9. Okay. One more question in electrostatics before we finally move on to modern physics. I'm just sending it. This one is a logical question. So just read through it, all of you, then we'll discuss. Yeah, so just go through this question. I've just sent the one with the two spheres. So it says two charged spheres are kept at a finite center to center spacing. The force of electrostatic interaction between them is first calculated assuming them to be point-like charges at their respective centers. And then the force is measured experimentally. If the calculated and measured values are this much and this much, which of the following conclusions can you certainly draw? Okay, so let us understand this in two regards. Okay, so first of all, let's assume that the two spheres, suppose they have actually like charges. Okay, so suppose this is having plus q1 and this is having plus q2. Then what will happen is that because of repulsion between them, the charge will get displaced. The charge will not be uniformly based on the sphere. Okay, so this will be the actual force. This will be the measured force versus the calculated force would be the similar diagram but assuming uniform distribution of charge. So the calculated value of force would be as if they're acting at the centers. So you can see that in this case, the calculated value is greater than the measured value because this charge center is moving further away. Right. So FC is greater than FM for like charges. Okay. And we'll see why it becomes less for unlike charges. Okay. Now the thing is that should this scenario be affected by whether or not the materials are conducting? So the answer is yes, it is affected, but it's not affected in the nature of the forces. It's affected by how much the force changes. In the case of conductors, this redistribution of charge will be more pronounced. Okay. And in fact, what will happen in the case of conductors is that most likely the charge will separate out so much that there might be some negative charge that appears on this side also. But still there will be repulsion, and that actual repulsion force will be less than the repulsion assuming they are like point charges at the center. Whereas in case of insulators, that redistribution of charge will be less pronounced. So the difference in the actual versus the measured, the actual versus the theoretical force will be less. Okay, so it should be irrespective. The behavior should be irrespective of whether or not they are made of insulating materials or conducting materials. Okay, now let's take the case where one is positively charged and the other is negatively charged. So here the induction will result in this kind of situation. The charge will come closer. Okay. So the actual charge centers will become like this. So the attractive force will become more in the case of measured value, less in the case of the theoretical value where it is like this. So in this case, F calculated will be less than F. This thing. This is for unlike charges, and this is for like charges. And this is irrespective of whether it is metal or non or insulator, both. But in the case of metals, this effect will be more pronounced. Okay, that's the only thing. All right, so these are the questions I wanted to discuss before we start with the modern physics question set. Okay, so now I'm moving on to that. So Aditya, I will start with the H.C. Verma questions you have asked, but I've also got a set of questions that I want to discuss. So let's come to structure of atom. And Ashwin, your questions also I'll come to. So let's come to structure of atom, Bohr's model of atom. That is question number 17 from H.C. Verma. Okay. So people just go through the question from H.C. Verma once. We'll discuss. So this should be page 385 or so, 84, 85 something. 384. Okay, so let's understand this question. Now this type of question is very important in the application of Bohr's model of atom. So this is H.C. Verma. Bohr's model of atom chapter. Page 384 in my edition. Mostly it's always the same. So question number 17. So it says that a gas of hydrogen-like ions is prepared in a certain excited state E. Okay, so let's say it's some kind of hydrogen-like atoms. So we don't know which state it is in. Okay, but E naught will be minus 13.6 into Z square. That much. Okay. Now it says that it emits photons in a particular excited state. It emits photons having wavelength equal to the first line of the Lyman series. Okay, so the first line of the Lyman series is which line? This line. Okay, so from excited state, it creates this together with 5 other wavelengths. So the total number of wavelengths emitted are 6, because it's this one plus 5 others. Okay, so that means the number of transitions possible okay from higher state or excited state to lower state. Okay, so from the initial excited state A to any lower energy state, okay, that is equal to 6. Okay, so if the excited state A has principal quantum number n, okay, then nc2 is equal to 6, or n into n minus 1 by 2 is equal to 6. So that means n is equal to 4. So this is the third excited state. Okay, or the principal quantum number is 4. Okay, so there are all these possible. These are all the transitions which are possible. Okay. So 3 to 0, 3 to 2, 3 to 1. Okay, then also this. Okay. So these are the 6 transitions which are possible. So principal quantum number is equal to this thing. is n equal to 4. I'm not sure how we are going to identify the gas here because there's no other information given. Okay, so I'm not really sure. It seems like some information is missing. So we can't really find out we can't find out the Z of this particular gas. The answer they are saying it is helium, but there's no other hint given. Okay. But Lyman series of what? That is the thing. If it says Lyman series of hydrogen, then it's one thing. Lyman series is a general term of transitions back to ground state. Okay, so you're considering that first line of Lyman series they're saying is the first line of Lyman series of hydrogen. Yeah, then you can do that. So if you interpret this way, that it's saying that it's emitting a photon of first line of Lyman series of hydrogen atom. So that means this E3 minus E0, this one should have the same energy as the first line of Lyman series of hydrogen. Then you can do this. Okay. So you can see that 13.6 into Z square. So we cannot be sure which one it is. So some N1 minus N2, this one. This is exactly equal to 13.6 into 3 by 4. So we assume this, then we will see that this fits for Z equal to 2, N2 equal to 2, and N1 equal to 4. Okay, it will not fit for any other transition. Like what we can do is see from this we have already found out that the higher quantum state is 4. So for N1, N2 in this, we can try all combinations. All combinations from 2 to 4 and N2 equal to 1 to 3. We can try all these combinations. We'll see that it will fit only for this. So that means Z has to be equal to 2, and this particular photon going from the third excited state to this first excited state, this middle one, this will give you the energy of the first line of Lyman series. Okay, so Aditya, is this clear? So I'll just explain what I'm saying here. That see, first of all, you are getting that there are 6 different photons, 6 wavelengths. Okay, so that calculation NC2 is equal to 6. This is showing you that the initial excited state is n equal to 4. Okay, or the third excited state. Now, no, it shouldn't be. They should mention actually. Okay, now what I'm saying is that assuming that they had mentioned that this is, now the other thing they're saying is that one of the wavelengths matches the wavelength of first line of Lyman series of hydrogen atom. Okay. In general, this should be mentioned hydrogen atom. We cannot make an arbitrary assumption like this. I'm saying that since he has not mentioned anything over here, let's just try to guess that okay, it meant hydrogen atom. So that means what is happening? Z square into 13.6 into 1 by n2 square minus 1 by n1 square should be equal to 13.6 into 1 minus 1 by 3, sorry, 1 by 4. Okay. For one of the transitions. Okay. Yeah, Ganesh, that's what I'm saying. That it seems to be the case that here you should default. But as I'm saying that ideally it should be mentioned in the question. They're talking about Lyman series of hydrogen atom. Okay. So anyway, so for this transition, so for one of the transitions out of all of these, that n2 equal to 1, n1 equal to 4, n2 equal to 2, n1 equal to 4, n2 equal to 3, n1 equal to 4, then n2 equal to 1, n1 equal to 3, n2 equal to 2, n1 equal to 3, and n2 equal to 1, n1 equal to 2. These are 6 of them. Now out of 6, one of these put in this formula should match this. Okay, so you'll see that the only one that matches is when I put n2 equal to 2 and n1 equal to 4. Okay. It matches for z equal to 2. So if you put each values, each set over here and try to calculate for z square, you will not get a whole number square unless you take this set. And when you take this set, it matches for z equal to 2. So that means z must be equal to 2. So it must be helium. Okay, so a bit of a weird question, but that's the way it is. So Ganesh and Aditya, hope the question is clear to both of you. Okay, next we are moving on to question number 19. So 19 is saying in a spectroscopic instrument, we can resolve two nearby wavelengths only when lambda upon delta lambda is smaller than 8000. Okay, so what does that mean? It means the fractional change should be greater than 1 by 8000. Basically, that is what it means. Okay. Just go through the language of question 19. Means the condition for resolving two wavelengths, suppose one is lambda 1 and the other is lambda 2, the condition is that lambda upon delta lambda should be less than 8000, or in other words, delta lambda by lambda should be greater than 1 by 8000. So basically lambda 2 minus lambda 1 upon lambda 2 should be greater than 8000. I mean, should be greater than 1 by 8000. Okay. So now you just apply this condition for the given series. Which series they are talking about? Balmer series of hydrogen. So for Balmer series of hydrogen, you have 1 by lambda is equal to Rydberg's constant into 1 by n square, where n is so on and so forth. Okay. So actually we can do this like this, that so basically just calculate the values of lambda for the Balmer series and see which of them satisfy this. Yeah, it is a very long question. It's not feasible at the JE level. Okay, next let us move on to question number 35. Okay. So question 35 in the same exercise, it says a neutron moving with a speed of v strikes a hydrogen atom in ground state moving towards it with the same speed. Find the minimum speed of the neutron for which the inelastic collision may take place. Okay, so here what we'll have to assume now, the energy lost in the inelastic collision is converted into transition energy. So this is your neutron moving at some speed v naught. This is your hydrogen atom or hydrogen ion. Okay. Now this is moving at the same velocity, right? In the opposite direction. Yeah. Now find the minimum speed of the neutron for which the completely or partially elastic collision may take place. Okay. So if we assume that there is maximum loss of kinetic energy that will occur for perfectly inelastic collision. Okay. And in this case, two bodies of same mass, okay, if they get stuck together, the final velocity will become 0. So the loss in kinetic energy for E equal to 0, perfectly inelastic collision. So the loss in kinetic energy for the system will be equal to half mv square plus half mv square. Okay. So this should be equal to transition energy. And the hydrogen atom was initially in ground state. So mv naught square should be equal to E1 minus E0, or at the minimum. This is a minimum condition. Why it is the minimum condition? Because first of all, we have taken perfectly inelastic when the loss in kinetic energy is maximum. And secondly, we have also taken that transition energy to be the minimum possible, which is the first line of the Lyman series energy, going from ground state to the nearest excited state, which is the first excited state. Okay. So now in this, you have to just substitute this, first of all, convert electron volts to joules. So mass of this is 1 atomic mass unit basically. So it is 1.67 into 10 raised power minus 27 kg. Okay. And 13.6 electron volts you can convert to joules. Okay. So do that and convert this, get this V naught in terms of meters per second. Okay, we have taken the mass of neutron to be equal to the mass of hydrogen atom as instructed in the question. So hope this is clear, Aditya. Okay, let's move on to 46th question. Yeah, so in 46th question, we have an excited hydrogen atom in state N moving with the velocity V. Okay, so we have an excited state N. Okay, now what happens is that it emits a photon in the direction of its momentum and changes its state to a lower energy state. So now let's say its velocity becomes V prime. It lowers, it comes to a lower state, lower excitation state of M, and it also emits a photon like this. Okay, so we have to calculate, apply momentum and energy conservation principles to calculate the frequency of the emitted radiation. Compare this. Okay, so now the thing is, this photon is of frequency mu. Now the thing is, we will not be using that, the general principle that the transition energy is equal to the energy of the photon. Rather, we will be using the conservation of total energy. So half m v square should be equal to, sorry, half mv square plus the energy of the atom which is in the nth state. This should be equal to half mv prime square, okay, plus energy of the mth excited state plus h mu. Energy of photon is h mu equal to hc by lambda. Okay, so that is one equation we have. Okay. And the other equation we have is momentum conservation. That is mv should be equal to mv prime plus h by lambda. Okay, so h by lambda can also be written as h mu by c. So we have this second relation. So we have to find this or this from second equation, and this is from equation 1. Now we have to compare this mu with the mu we would have got in the normal situation if the atom were at rest. Okay. So if the atom were at rest and we took the normal situation, then this energy should have been h mu naught. So just replace this with h mu naught. Okay, so Aditya, I hope the method is clear. So comparing this situation where you're doing momentum conservation and energy conservation like this with the standard situation where you just assume an atom at rest emits a photon where the photon energy is equal to the transition energy. Okay, so this completes these Bohr's model questions. So we'll just take a short break and we'll continue with more doubts after this. So let's take a break now. Okay, people, let's resume. So I have one more doubt from HC Verma before we'll move on to Ashwin, your set of questions from the module. Okay, so question 21 from X-rays. Let's look at this one. So this is basically got to do with the concept of cutoff wavelength, or maximum energy of X-ray photon that we can get. So it's saying that so this is X-rays chapter from HCV. It's on page 395 in my book. Okay. Question 21. Okay, so it's saying that we have a tungsten target, and the energy in keV of cell containing vacancy in tungsten. So for tungsten, it is saying that the energy of cell vacancy, that means the energy we need to supply to remove an electron from a certain cell, for K shell it is 69.5 keV. Okay. And for L shell it is 11.3 keV, and for M shell it is 2.3 kilo electron volts. Okay. Now I'm saying that energy levels of the shells are given. Okay, actually these energy levels are given, but they should be negative energy. So if you're talking about this in terms of energy levels, they should be minus, minus, and minus. These are the energies of electrons in these particular shells. Okay. Whereas if we are talking about the energy required to create a vacancy, then that will be that positive energy. Okay. So anyway, now it's saying that what is the maximum value of this thing, the accelerating potential, maximum accelerating potential V, such that characteristic K and L, this thing lines, are not in the X-ray spectrum. Okay, so we know that from this we'll know that the K alpha, K beta, etc. series will have energies and lower. Similarly, we know that, so for example, the K alpha line you can see will be 69.5 minus 11.3 keV, and this is the lowest energy of the K series. Similarly, the L shell, so the L alpha, L beta, etc., will have energies of 11.3 keV and lower. Okay, so the minimum one will be L alpha, and this will have an energy of 11.3 minus 2.3, that is 9 kilo electron volts. Okay. So that means our incoming electrons should be of such energy that they're not capable of, okay, they're not capable of ripping out either K shell electrons or L shell electrons. Okay. So to avoid the K and L series of characteristic lines, okay, the maximum kinetic energy of a, of a colliding electron should be less than the energies of orbital electrons in K shell and L shell both, so that you're not able to rip out these electrons. If you can't rip out these electrons, then you will not get transitions from higher energy state to K series or higher energy state to L shell. So those particular wavelengths will not be emitted. Are you understanding? So now you can see the condition for this is L is the lower one of the two. No? It was 11.3. So this Ke max of the incoming electron, which is nothing but electronic charge into potential difference, should be less than the energy of the L shell, which was 11.3 electron volts. So basically, V should be less than 11.3 volts. Okay, it's okay that the minimum energy of L series is L alpha is 9 kilo electron volts, but that's not the point. To generate this, we first need to make a vacancy in the L shell. So to create a vacancy in the L shell, we need a minimum kinetic energy of 11.3 electron volts. Okay, so hope you've understood this. Yeah, Aditya, see why we didn't take 9 is because 9 is the energy that you get when there is, just a second, guys. This is the energy that you will get. 9 kilo electron volts is the energy that you will get when this happens. When this transition happens, it will give a photon of energy 9 keV. But the thing is, first we have to create a vacancy here. No? You understanding, Aditya? You have to create a vacancy in the L shell so that such a transition can happen. So to create that vacancy, how much is the minimum energy you require? I mean, how much is the energy of the incoming electron you require? It should be greater than equal to 11.3. No? You understanding? You need to ionize it. No? So basically, it is like the ionization potential for the, that's why. So if your incoming electron only has energy of less than 11.3 electron volt, it will never be able to rip out an electron from the L shell, let alone the K shell, because for K shell, it requires even more energy. Okay, so it should not have energy of more than 11.3 electron volts or even 11 equal to 11. It should have energy less than 11.3. That's why. Okay. Yeah, I'm moving on to some more doubts now. Just give me a second. Yeah, now this is an interesting question. Just explain it to all of you. So it says that a neutron collides with a stationary helium atom which is at ground state. So we have an He plus ion in ground state, which is stationary. Okay. And this is collided by a neutron. So neutron comes and collides with it. Now it's saying what should be the minimum energy of the neutron so that all types of collisions, that is elastic, inelastic, and perfectly inelastic, can take place. So what should be the minimum energy of the neutron in electron volts so that all types of transition types of collision, that is elastic, inelastic, or perfectly inelastic, can take place. And as usual, we have to take the mass of the helium ion as 4 times the mass of the neutron. So that is the thing. Now we have to find the kinetic energy. No? The helium ion is initially at rest. Okay, Aditya, understood now? The helium ion is initially at rest, but the neutron, the energy we're talking about of the neutron is the kinetic energy only. No? It's not. So this is not going to be okay. Right. Okay, and the helium ion is in ground state initially. So the minimum transition energy for the helium ion in ground state, the minimum transition energy, say delta E minimum, will be for transition from ground state to first excited state. So that is Z square into 13.6 into 1 by 1 square minus 1 by 2 square. So 4 into 13.6 into 3 by 4 electron volts. This is the minimum transition energy. Okay. Whereas for the incoming neutron, suppose it's coming in at V naught. Okay. The maximum loss of kinetic energy will be for perfectly elastic collision. Perfectly inelastic collision. So for perfectly inelastic collision, after collision, this becomes some kind of an isotope, you can say. Okay. Because that neutron would be inside it, but going at some speed v. So 5 mv should be equal to mv naught. So v is equal to v naught by 5. And final kinetic energy would be initial kinetic energy by 5. Okay. So loss in kinetic energy would be 4/5 of half mv naught square. So this loss in kinetic energy should be greater than equal to the minimum amount of transition energy that is required. Okay. So this should be answered in electron volts. They have taken n equal to 3 for transition. So basically they've taken this number instead of 3 by 4, they've taken it as 8 by 9. Right, Samadip? They've replaced this with 8 by 9. Okay. Let's go over the question once more. Let's try to understand. No, but this condition that we have found out is for one of the three things. It said that all types of collision. Okay. This is for perfectly elastic. Sorry, for perfectly inelastic. Collision. We have this first condition that we have got. Okay. But what for partially inelastic? We want partially inelastic. No, so Aditya, see, the whole point is that the energy lost in collision has to go into transition here. Okay, that is something understood in these questions. Now, whenever we are dealing with collisions at the at the atomic scale, this is what we have to assume. Okay, I mean, yeah, many times you'll see in JE papers the question gives you that hint that assume that the kinetic energy dissipated is going into transition energy, but otherwise also you'll always have to take that as the standard assumption. Okay, now let's also talk about what happens if you're doing now. See, with this amount of energy, is partially inelastic possible? No, because partially inelastic will give you a loss in kinetic energy for E greater than 0 but less than 1, which will be less than this now. It will be less than 5 by 4 into 4 into 13.6 into 3 by 4. So that won't be possible. Okay. So I think what the question means is that what kind of energy we should give, that all three types are probable. So, this has to have some kind of energy where now based on probability, perfectly elastic is also possible. Okay. So that is for any value of half mv naught square because there's no loss of kinetic energy. Okay. Now, for perfectly inelastic, what we have seen is that half mv naught square should be greater than that delta E minimum that we calculated, where delta E minimum greater than equal to was E1 minus E0. Okay. Now let's come to the third possibility for general inelastic collision. For general inelastic, what is the condition that, I mean, not this, the loss in kinetic energy. This should be greater than equal to, okay. Now for this, the loss in kinetic energy will be, now in the inelastic case, it will be less than this value that we calculated. This value will be less than this one. So the loss in kinetic energy will be less than 4 by 5 into half mv naught square. Okay, and this loss has to be still greater than equal to E1 minus E0. Okay, so now because there is no equality here, na, you can see this is greater than. So what is the condition that we are getting? That 4 by 5 half mv naught square has to be greater than E1 minus E0, not greater than equal to. You understand me? This is the condition for this. Okay. Now, for perfectly inelastic, what are the conditions possible that this loss is either equal to E1 minus E0, okay, or it is equal to E2 minus E0, or it is equal to E3 minus E0, and so on and so forth. Okay, so I want the minimum value such that this is also possible, but along with this, this is also possible. So for this, this has to be greater than this first term. So the next term which is greater than the first term is this one. So that is the kind of logic they've used in the question. Ideally, the question should have been a little bit better explained, but this is the kind of logic they've used in this term. Okay, so you have to get used to the language of these questions a little bit. Sometimes it can be tricky. Okay. I will also send you a worksheet of questions which are to do with photoelectric effect and Bohr's model, mix of concepts, where some of these kind of limiting condition type of situations are discussed, and we'll discuss that worksheet in the next lecture. Okay, so people, I actually have an appointment at 8:30, so I have to rush out. So we will conclude the class a little bit earlier today. Okay, yeah, some of the probabilities that, so for one inelastic probabilities, there is only if it is at least one energy difference. Yes, so basically, see now, I want that the loss in kinetic energy is greater than this quantity. Only then inelastic collision is possible. Okay, or basically, it's like this, that the loss in energy should be equal to E1 minus E0, but the loss in energy is actually greater than 4 by 5 half mv naught square, is less than this. Now my delta K loss, this thing's minimum value should be equal to E1 minus E0. But in the case of inelastic collision, this thing itself, this loss itself is less than 4 by 5 half mv naught square. Okay, so that is why my 4 by 5 half mv naught square has to become greater than this. So what's the next possible value for which I can get perfectly inelastic is this one. So for that value, perfectly inelastic will also be possible, but inelastic will also be possible. That's why. Yes, Ashwin, I will come to your doubts in the next one, definitely. Okay, I will send you some hints also. All right, we'll start. Okay. So wish you all the best, people. Until the next lecture.